Hello and welcome to a lecture about the relationship between the Alexander polynomial and sums. This is an account of the proof of Theorem 5.8. Or, well, it's not really an account of the proof, it's a sort of a description of the proof and hopefully will help you to understand it. So, what does the theorem say? The theorem says that the Alexander polynomial of a sum of two oriented knots, j and k, that's equal dot, so not strictly equal to, but equal to up to sines and powers of t, equal dot to the product of the Alexander polynomial of j and the Alexander polynomial of k. And so the Alexander polynomial of a sum is the product of the Alexander polynomials. And I'm going to demonstrate how the proof works in the case of the sum of two trefoils. So look now at these two knots here. What are they? Well, they are trefoils. Let's draw one of the trefoils. Here. And observe that I've taken a normal diagram of the trefoil, that's what's on the left there, and added in a kink using Reidemeister move 1. And similarly in the right hand side I've taken a normal diagram of the trefoil and added in this kink. So that's the first stage of the proof of this theorem, is take diagrams of j and k and place into them this extra twist, which is kind of important for making the proof work. Now, so what do we have on the left hand side of the page? I've got the diagram of my original oriented knot j. I've placed this kink into it, and then I've numbered the crossings 0, 1, 2, 3, starting with the sort of new crossing is 0, and I've labelled the arcs x0, x1, x2, x3, and I've made sure that x0 is the arc that goes over 0, and I've made sure that x3 is the other arc that's next to 0. And I did the same thing on the right with k. Taken a diagram of k, placed this twist into it, labelled the crossings 0 prime, 1 prime, 2 prime, 3 prime, starting with 0 prime being the new one, labelled the arcs y0, y1, y2, y3, with y0 being the arc that goes over 0 primed, and with y3 being the arc next to 0 primed. Okay, and then what I've written out here for you is the matrix of coefficients of the polynomial colouring equations, then the polynomial colouring matrices themselves, and those are A and B, and then their determinants are the Alexander polynomial of j and of k respectively. That was a disaster. Let's try again. There we go. So now what do I have on the right? Well, I have the knot j sum k, and I formed it by joining the edges of the extra twists together. Then what have I done? I've named the crossings. I've kept exactly the same names of the crossings in j. And I've kept the names of the crossings 1 prime, 2 prime, 3 prime in k. And now this crossing that used to be called 0 primed, I've called it zeta. That's a zeta. Whoops. Let's get this right. That's a zeta. Because it's going to come at the end and I'm going to kind of ignore it. What about the names of the arcs? Well, the arcs that are well inside j, in other words, everything except x0, I've kept the name for x1, x2, x3. The arcs that are well inside k, y1, y2, y3, I've kept their names too. Now, you can see that arcs x0 and y0, they've been kind of fused together, and I'm going to call the resulting fused together arc x0 equals y0. And then what used to be part of x0 and used to be part of y0 has now been detached, so I give it a new name, z. And I've written out down here for you the matrix of coefficients of the polynomial colouring equations. And I've done it by ordering the crossings 0, 1, 2, 3 from the original j, and then 1 prime, 2 prime, 3 prime. So let me draw in 0, 1, 2, 3. 0, 1, 2, 3 from the original j, 1 prime, 2 prime, 3 prime from k, and then zeta at the end. And how have I ordered the crossings? Well, I've started with x0 equals y0, followed with the rest of the x's, followed with the rest of the y's, and then on the end I've tacked z. And you can believe me that these are the coefficients from the polynomial colouring equations. So now let me write down the matrix whose determinant will be the Alexander polynomial of j sum k. I'm going to do it by deleting a row and column. And I delete the first row and the first column. So let's do that now. There we are. And I'm going to call that C. Now, what do we notice about C? We notice that we can divide it up in a nice way. That's going to be very helpful for computing the determinant. If I break it up across these two lines, then what do I have top left here? What I have top left here is a copy of A. So maybe I should write that in. That's a copy of A. Yes, it is. Good. What do I have elsewhere there? I have zeros, so that's good as well. Next, what happens? I'm going to divide it up across this line and across this line. So then observe that what I have in this box is a copy of B. Yes, it is. That happens also to be the same as A, but morally it's a copy of B. And then what's left, apart from those two things, I've got a T down the bottom, and I've got a -1 there. But this is enough for us to work out the Alexander polynomial, because now the Alexander polynomial of j sum k, that's the determinant of C. Now, what is C? It's a block matrix, which is block lower triangular. So it's divided into blocks. The diagonal blocks have things in them. The things below the diagonal blocks may have things in them. That's this -1 here, right? That's below the diagonal. But above the diagonal, that's in this box, and this box, I have all zeros. So it turns out that in that circumstance, the determinant of the big block matrix is the product of the determinants of the diagonal matrices. So it's the determinant of A times the determinant of B times T, which is, what's that? I need more space. Let's make more space. We've left the B behind, but never mind. There we go. So that's equal to, well, det A is delta JT, det B is delta KT, and T is T, but that's all equal dot to delta J, T, delta KT, which is the product we claimed. So that's why we get the product in this case. And I'm going to end the mini lecture with some questions. The questions are about the matrix C. So first question, why don't I number these questions actually? Let's number them. Why are the, oh dear, let's number them 1, 2, 3, 4. So the first question is, why are the I, yj entries 0? The I, yj entries are the ones with the rows coming from J, but the columns coming from K. So this is here. Question 1 is about these entries. Why are these all 0? Then question 2 asks you, why are these all 0? This is question 2. Why are the I prime, xj entries all 0? And I should divide my matrix up a bit more. Question 3, why is the ixj part exactly A? So question 3 says, why is this exactly A? And question 4 asks you, why is this exactly B? So I want you to go back to the previous screen, so rewind the video, look carefully at all the diagrams we had, and decide why the matrix C has the features just described. And then, after everything, ask yourself the following general question, which is, would the proof work without the trick? Would it work without the trick? What was the trick? The trick was installing these little twists into our diagrams at the very start. Would it work without those? Okay, so that's the end of the mini lecture. Good luck with the questions.